Yeah, I just stapled them together, so they're all on there. Okay, good? Okay. All right, well, welcome. Okay, we're coming up on the final exam, and unfortunately for you guys, you've got it on Monday morning. Fortunately or fortunately, you'll feel better after it's over. A lot of students wonder what to do. We've had a long semester as far as getting ready for the final. You haven't got much time, and you've got other finals to go over, so and prepare for. So I would say, for the most part, focus on your hourly exams. Also, these practice problems that I've been handing out, you should check those. If you're missing any, I've got a few extra copies from past reviews. So hopefully you've got those, and that's a pretty good base to work from as far as getting prepared. Most people don't have enough time to then go on and get back into homework, but I prioritize it that way as far as studying. As far as this review is strictly on chapter 13 and 14. He's promising you what, 1 or 2 problems? 2 problems. One from each chapter. Some of this stuff ties in with stuff earlier, so in a sense it covers more than just 13 and 14, but it's ideas you definitely want to have a grasp of. We're going to start off with just gravitation, and the idea of the gravitational force between two masses, let's say M1 and M2. We say that there's going to be a force of attraction between them. And that force is action-reaction. They're equal and opposite. And that force is going to be equal to the universal gravitation constant, big G, times the mass of one, times the mass of the other one, all over the distance squared between them. And that distance is really the center-to-center distance, as long as they're spherically symmetric. And usually when we deal with planetary problems, you measure from the inner part of the planet out. This idea isn't entirely obvious. Newton kind of thought it intuitively. He had to invent calculus, and after 19 years he finally was able to prove this. But the idea is this. Suppose you've got something like the Earth here. Let's call that, let's say, mass of the Earth. And we've got something smaller. Let's say maybe I should make it a red apple, like Newton's proverbial apple. That's mass m. And there's going to be an attraction to this mass of the Earth. Now, this attraction depends where you're at. Some places over here are closer, and there's going to be a stronger attraction to these little bits of matter. As compared to over here, they're going to be more distant, but they overall will, maybe I'll just leave it at this, that there's going to be more of them over here. They're pulling, but they're a greater distance. It turns out that it's equivalent to doing this, taking the whole Earth and crunching it down to a single point of mass m. And then this apple is out here, sitting out here, some distance, the radius of the Earth away from the center. And the idea that it's attracted to that, and the center of the Earth would also action-reaction, and that's the force between them. And the proof of this, Newton went through. We don't do it anymore. The book alludes to how we set this up. It's not a super difficult problem, but we're running out of time. But it's important that you understand the idea that if we're dealing with the gravitational force of the Earth, and we say, wow, it's sizable, if I have this apple and I let go, it should fall. Now, what we've been dealing with so far is that force of gravity. We say that force of gravity is equal to mg. That's what we've been dealing with. But we also know now with universal gravitation that force of gravity should be equal to big G m1 m2 all over r squared. Oh, excuse me, I'm going to do this. I'm getting a little ahead of myself here. let me change this to being M1 would be, let's say, the mass of the Earth. And then let's say the apple is just a small m, so that will be M2. And then all over the distance between them, if they're close to the Earth's surface, this is going to be the radius of the Earth squared. And so that should be the gravitational force according to gravitation. Now we know that already that we've been dealing with this, that it's equal to mg. Just F is equal to ma. We know that the apple will fall with gravitational acceleration of g. So we can set these two things equal, and we can cancel this m. And so if I have big G, mass of the Earth, all over the radius of the Earth squared, that should be equal to g, which we know is 9.8 meters per second squared. And as long as I know that, and if I know the universal gravitational constant, I didn't put that up here, you might want to pack this away, although he probably would give it to you in the exam. This is going to be 6.7 times 10 to the minus 11th. And this is going to be, it's got to be in newtons, and then it's got to be over kilograms squared, since it's going to be kilograms. We're going to have a radius here, so there's going to be a meters squared. Don't worry so much about the units, other than maybe do everything SI units, and then you don't have to worry about all this unit stuff. So that's the best way to deal with that. Anyway, since we know this is 9.8, and if you know the gravitational constant, you can then use this to calculate the mass of the Earth. And that would be the idea for that. How about if you have the Earth and you're out some distance away? Let's say you've got the radius of the Earth, and let's say you're twice that. They'll talk about the altitude up here. That's got, and if it's at the altitude of the radius of the Earth, it's still got gravitational force on it. We might say that we've got a different force, that it's going to be big G. It's going to be the mass of the Earth, again, times m. All over the radius of the Earth, there's going to be 2 of them, and so we're going to square that. And so we end up with 1/4 of big G m all over the radius of the Earth squared. And so that's going to be 1/4 the force. And then that's going to be equal to some mass times some acceleration. It won't be g, but we could say that it's, let's say, g prime. The acceleration of something, if I had a rock up there and I released it, it would fall, and that would be the acceleration that it would start to fall. We could see then that this was 1/4 of all of this at the surface of the Earth was just g is equal to g prime. So we're going to end up with 1/4 the gravitational acceleration. Something will still drop. The fact that you're out in outer space and there's no air around, think of yourself as just floating. You're not going to just float. You're going to fall. You're going to start to fall towards the surface of the Earth. Now, in order to keep from, let's say, falling, we need to go into orbit in order to keep ourselves up there. And let me erase this. And if I want to put something into orbit, we have to give it enough velocity. So I'll have, excuse me, I don't want to, well, let me make that my orbit. I'll make this, I'll call it just capital M. It could represent the mass or any kind of planet. I'm going to have some satellite, either artificial or terrestrial, that's going to orbit the Earth. It has to go at just the right velocity. And if we're going to get it to travel in a circular orbit, we have to have precisely the right velocity to travel in a circle, because we have to have an acceleration that's going to be v² over r. So the idea that there's still this gravitational force, still big G, big M, small m, all over r squared. That has to equal the acceleration, good old F equals ma. This is the force, the mass, and the acceleration, if it's going to travel in a circular orbit, has to be v squared all over the radius. So from this I can do some canceling. I can cancel the m's. I can cancel one of the r's. I could take the square root of this, so the velocity is equal to square root of big G m all over r. Now this is the velocity that would be needed for a circular orbit of some radius r. Notice that the velocity depends on what the r is. The larger the r, actually the smaller the velocity. As you go further out, it doesn't take as much to keep moving to keep it in a big circular path. Now, if your velocity is any different than that, if we, let's say we fire a rocket burst and we speed up in this direction, then we're going to take off and go out, and we could use that to get up into a higher orbit. If I slow this thing down, it could fall in and go into a lower orbit. But so the idea that this is the orbital speed for a circular orbit, that is going to be precise. Something we can do here also is, once we have that velocity, we can also figure what's called the period of this thing. How long does it take to go around? The idea that we're playing with is just basically distance is equal to velocity times time. The distance to go all the way around is going to be 2 pi times r. That's going to be d. The velocity is going to be, has got to be this, square root of big G m over r, if it's going to travel in a circle. And then t would represent the time to go around once, and that's what we'll call the period. So I'll call that capital T, standing for the period of rotation around this. And we can play with some things, just changing the form of this a bit. What I'll do is let me square both sides to get rid of this nasty square root. Squaring this is going to be a 4 pi squared. R squared is equal to, again, we square this, we get rid of the square root sign, and then we're going to have the period squared. And what we can do is change some things around here. I'm going to bring one r up here. This is going to become r cubed is equal to big G m, and then I'm going to divide that by 4 pi squared. And then this is going to be the period squared. Usually we'll write this way, that the period of this thing, I'm going to put it, the square of the period is equal to 4 pi squared all over, I'm just taking it over to the other side is all I'm doing, times r cubed. And this relationship is what they call Kepler's third law, at least for circular orbits, that the square of the period should be some constant, a proportionality. The square of the period should be proportional to the cube of the radius of the orbit. Okay? Now, we're going to do, and we've done just really the math for a circular orbit. A more general case is an elliptical orbit, where you're going to have an ellipse. And I think Dr. Young showed you how you can make an ellipse with a couple of points here called foci. If I could drive some nails in here and put a string around this, I could trace out an ellipse. And I've got this a little bit lopped here. And this is actually going to be the closest point, and this is going to be the furthest point. And the idea that this would be the radius of, let's call it R1, would be just out to here. And out to the farthest point, we could call R2. And what we'll frequently do as far as doing problems with this, we look at the ellipse. It's really symmetric. It doesn't look like this way here with my picture, but we'll divide this thing up cut it in half, and we'll just call this A is this distance here. So it's called, this A is called the semi-major axis. And this is a length. And actually, without proof, the book asserts that if you want to have a more general form for Kepler's third law, we'd say the period of the orbit is equal to 4 pi squared all over big G m. And then instead of r cubed, it's going to be a cubed, and that will work the same. And this does hold. This is not so easy to prove as it was for a circular orbit, but it still holds for our cases. So some of the problems, generally I think Dr. Young has not really done much with elliptical orbits. You do have some problems in your homework where you have them, and so I think I'll just put that in. And but likely for the exam, he'll keep things to circular orbits. These are things you can directly derive. This is something you just have to take on faith for what we're giving you. Okay, let's see if I caught everything. Okay, I think I wanted to do that. Okay. Okay, let's look at another aspect. Right now we've been talking so far about like the forces that are working here, the gravitational force pulling on the two of them. And we're playing with F equals ma, and so all of this is sort of what we would say would be the Newtonian method for this. Let's look at it from the point of view of energy. If I'm going to, because energy principles, as you know from the past, are usually very handy if you can take advantage of them. Let's look at something like, it could be the Earth or any planet. And we want to go from, let's say, some point. It could be on the surface of this thing, or it could be out in space. I'm going to want to go from some distance, let's say R1, again measured from the center of this thing out to here. And let's say I want to call this, let's say maybe instead, well, R1. That'd be like my initial point. I want to go there. And then let's say I want to lift something away. Let's say I've got an object of mass m. And of course, gravity is pulling in on this thing. Force of gravity, and of course this is pulling back. Whoop. Okay. And if I want to, let's say, lift it from some R1 out to a further distance, lift it up and out in an orbit, I've got to go some R2 to lift it further. And if I'm going to do that, if I want to move it out, I've got to apply an external force to this thing. So this is, the force of gravity is pulling back. And if I want to lift it out to here, I have to apply, we say, an external force to move it. Now, this gets a little confusing, and sometimes the derivation bothers people. I would say look at it from the point of view of, let's say, flat Earth. Just to kind of remind you, good old days when the Earth was flat, you'd have the ground would be like this. If I had some kind of a box or something, and I wanted to lift it up to some height, we'd say, well, it goes up some h, and I'd say that the potential energy is going to be equal to mgh. But now look at what the forces are doing. When we're lifting this thing, gravity is pulling down with mg. I would have to, as an external force, apply an opposite directed force, I'll call that the external force, to lift this thing up. Now, the work gravity does as I move up, and the idea that displacement is in the positive sense, so I'm going up some distance h, I'm going together. The work the external force does is equal to the external force, which would be equal in magnitude to the weight. I'm just going to lift it up, let's say at a constant velocity. That force times the distance I move, h, and that's equal to my change in my potential energy. The work gravity does is actually the negative of that. The displacement's this way, gravity is down, so it's equal to a minus change in the potential energy. So this notation is still with us, and the basic idea of this can be helpful in that the idea that if I want to lift this thing away, it's analogous to lifting this thing up here. Now, of course, here this is fairly simple because we have a constant force times a distance. I don't have to do anything like integrating. However, this I do. I have to stop and think. I'm going to do a little bit of work as I move this thing out, and the idea of that the work the external force does, doesn't look like a work, is equal to the integral of the force, which would be equal to the force of gravity, times dr as I move this thing out. And I'm going to integrate from R1 out to R2. The force due to gravity is, again, back this way. I'm going to apply it in the plus direction. It's just a little easier to deal with than with the signs. And so the magnitude of it is a big G m all over R squared. Again, from R1 out to R2. When we integrate this is going to be a negative big G m, not over R squared, but R to the minus 1. Remember, this is R to the minus 1. If I take the derivative of that, the minus 1 makes that positive, and then that R to the minus 1 goes to R to the minus 2, back to here. So hopefully you can see clearly that this is the integral of that. And we're going to evaluate it from R1 to R2. So we would say it's going to be equal to a minus big G m all over R2. Minus and minus will become plus big G m all over R1. So that would be kind of the integration of that. Now, back on flat Earth, remember we'd say, okay, this is the potential energy at that point. Now, in reality, the change in the potential energy is equal to the work done. And so this is the change in the potential energy. Maybe I'll put it over here just to emphasize that. This is the fundamental idea. And usually when we're doing energy, ultimately all we care about is the change in potential energy as I go from one place to the next. Back on flat Earth, we actually did the same kind of thing where we'd have the potential energy initial and the potential energy final, and we'd want to ultimately only care about how did the potential energy change. And that gave us this window of opportunity to just say, well, I'll just make the ground or some other level, I'll call that zero gravitational potential energy, and then do everything relative to that. Now we can do something like that here. Where do we make zero gravitational potential energy, though? And this is key. Ah, okay, that's right, yeah. A lot of people say, hey, well, let's make it on the surface of the Earth, just like all flat Earth, zero there. The problem there is you actually end up with a messiness. You could do that, but these equations are fairly clean. What we can do here is actually just define the potential energy. I want to do this mathematically, so I'm going to go big G m all over R. Okay, I don't need to worry about the subscripts because then I'll play with U1 and R1 and U2 and R2 and then worry about the difference between them. Oh, excuse me, I left off this important minus sign. Okay, now where would U0 be? Okay, Francis hit it here, but the idea that when R approaches infinity, what's going to happen to this term? Isn't that going to go to 0? So in terms of the math, the most convenient thing for us to do is define that way out here at infinity, that's the potential energy is going to be 0. Everything else coming in here is going to be negative. The closer and closer I get to this planet, the smaller this gets to be, and the bigger the potential energy. That is negative. This potential energy is still higher than this potential energy. It's further out. And so it's just less and less negative. So everything is kind of in the hole from here. It's 0 out here and anywhere in here. It just gets to be negative and larger and larger and negative coming back this way. Okay, I hope that makes some sense. I think as we get employing this and looking at some of the problems, once you have this idea, you're in pretty good shape. Okay, now what about for a circular orbit? Let's see. I'll probably come back to some of this, but let me okay, let's take a look at an orbit from the point of view of energy. If you're in orbit, and again, we're dealing with just a circular orbit for now, so the idea is if you're out at this point, you have a particular energy, and I expect that energy to be equal to the kinetic energy plus the potential energy, just like we've been doing. The kinetic energy should be 1/2 mv squared plus the potential energy, which will be a negative big G m all over r. And so that would be the energy of that orbit. Then there's something we can do. Let's see, I erased part of that. Maybe we'll review that again. Again, I want to get what the V is so I can plug it in here. I expect that from this idea that the force, big G, big G m all over r squared, okay, so that's the force that's into the center, has to equal the mass times the acceleration. The acceleration is in a circular orbit. It's got to be v squared over r. You want to do this derivation just a few times so you're comfortable with it. That knocks it off. We get rid of m, and we can get v, well, v squared. I could take the square root, but actually, if you think about this for a moment, you've got a v squared here, and I'd like to take this and substitute it in for my kinetic energy. The energy should then be 1/2 m, and for v squared, I'm going to put in big G m over r minus big G m all over r. Okay, now this is starting to, in fact, let me move this m inside here. Yeah, maybe let me do this. It's going to be a 1/2. Let me write this out and see if you're okay with it. Times big G m all over r. Okay, what I've done is, first I'm going to put that little m here. So I've got two terms that look like this. One with a 1/2, and then this is a -1. This is going to leave me with a negative 1/2. And I didn't leave myself much room here, but let me bring it up here because this is going to be key. That the energy, and this is the total energy for an orbit, is going to be a -1/2 of big G m all over r. So now keep in mind the big picture here. We'd still have the total energy as kinetic plus potential. This kinetic energy, though, it takes on a kind of a weird look. It looks a lot like potential energy, has the same form, and we end up with a minus 1/2 in front of it. So a lot of times people are confused. There'll be a 2 down here, and they want to know what's going on with that. Keep in mind, this is the total energy for a circular orbit. By total energy, that's kinetic plus potential, are both tied in together. They're all wrapped up in this single term. So if you have something in orbit, you can say its energy is this value. And let's see, what else? So that's going to be the total energy for something in a circular orbit. If you are worried about elliptical orbits, it turns out that you can, for an elliptical orbit, stick in an A in here. This semi-major axis will give you the total energy for an elliptical or any kind of orbit. Okay, so this is kind of the heavy-duty kind of theory that we're kind of jamming through, and Dr. Young took you through this, and hopefully this is you're seeing this the second time. It's okay. Let's do something that's important here, and he likes this idea as far as a test, is to talk about the idea of escape. If we have a planet here, and let me draw it down here. And you've got, let's say, a rocket ship that's going to take off, and we want to say escape. It's got to have a certain amount of velocity, and I want to find the escape velocity. Now, if you think about this, ordinarily, if I take something, and let's say a ball or something, and I throw it up into the air, it goes up, it hits some height, it's slowing down all the time till it gets up to that height, and then it's going to fall back. If I take this thing and I throw it harder, it's going to go up higher, stop, and fall back. Then the question is, if I took something and I threw it up with this speed, it would go up, slowing down the whole time, but the idea that it would get all the way out to infinity and finally come to rest. So out here, the potential energy is equal to 0, and also the top part of this projectile at the minimum speed to escape is going to leave us with a kinetic energy that's 0, and so the total energy has got to be equal to 0 to get out of there. Potential energies are all negative, kinetic energies are positive. If you can get enough kinetic energy, you can escape there. Let's look at this idea from the surface of this planet. It could be the Earth or any other planet. Call that big M. This is going to be small m. And then the idea would be we want the total energy. Total energy here, here's where I don't want to just say, oh, this is the total energy. It's not in orbit here. We need to go back to the idea that the kinetic plus the potential is the total energy. The kinetic should be this 1/2 mv squared. Okay, and this v we're hoping we want to show is the escape speed. That I'm looking for a particular v. The potential energy is a minus big G m all over the radius r. Maybe I'll use a capital R just to emphasize that it's not just an ordinary r. It's actually, we're taking off from the surface of a planet of radius r. And the idea that that energy needs to, if it's going to escape and get all the way out here, it needs to be equal to 0. And this is a key idea as far as having your total energy 0. That's going to get you out to infinity, where you can spend the rest of your days at rest. So we can, with this, it doesn't turn out, it doesn't matter about the mass of this thing. It might take more energy to take off with this thing. But I can solve for the escape velocity. I'll take this over to the other side. Is big G m, well, I got rid of the small m's, all over r. And then I'm left with a 1/2. I take that, let me take that 2 over to the other side. Is equal to the escape velocity squared, or I'll take the square root of that. And so that's the escape velocity from the surface of a planet. Now, you had and have a homework problem that has some different twists with this idea. One is the one with Jupiter and Ganymede. How many people have done that? Done that? Okay, taking a look at that. The idea that from that you had the mass of Jupiter, and then the planet or the moon around it is Ganymede, would be going around here. We've got a rocket that's on the far side of this thing, and you want to be able to escape that. So the idea is what you want to do is you're going to take off with a particular velocity, and you want to know what is that escape velocity that you want to take off with. The idea that you have different distances here, you're going to want to come up with your idea of your total energy. Your total energy is going to be your kinetic energy, 1/2 m, the velocity that you want to escape, squared. That's kinetic energy. But now we're going to have two potential energy terms. We're going to have a minus big G. We're going to have the mass of Jupiter all over the radius. Now the radius would be from here out to here. So this is, I'll just call it R of Jupiter. So it'd be the distance from Jupiter to Ganymede. Plus, if you want to include this, you're going to see that this is virtually negligible. But that would be that would be negative. But we're also escaping not only Jupiter, we're also escaping Ganymede. So there's going to be another term here, minus big G, the mass of Ganymede, all over the radius of Ganymede. And then the idea, if I want to escape, I want to set my total energy equal to what? 0. And so that's going to be key in doing the problem. Okay. Let's look at okay, yeah, let's these practice problems. Let's say actually I wish I had done that earlier. I had the equation up here for number 1, but I've already talked about it. So if you this get locked. Okay. How about number 2? I think this kind of takes us through kind of some steps here as far as being able to do some problems. And builds on the idea. The first thing we're going to want with number 2, how much energy is needed to lift a 1,500 kilogram spacecraft straight up from the Earth's surface to an altitude of 2 times the radius, Earth's radius. And it gives you the mass and so.
Can I just ask one question?
Yeah.
Before you erase that little box diagram on the right. So why is the mg times the height when it's you're trying to find the work of the external? Like the external force times the height?
Right, right. And the external force I was just arguing is going to be equal to the weight of this thing.
Oh, okay.
And so, yeah, I should have put that in first. External force, and then the external force is going to be the same as that. Okay. And then I can just lift it up at a constant speed. So it's, yeah, okay? Yeah, certainly conceptually I want that. And doing it from the point of view of the work the external force does, I think it's easier to avoid all these sign errors that come up. Okay, so let me hang on to this one for a minute. And so we're going to start off with, let's say we're here. We've got something, this was the Earth. Okay, so we have mass of the Earth. It's going to have the radius of the Earth. Let me just call that big R. And we want to lift off from a point that's radius of the Earth, and it says how much energy is needed to lift a 1,500 kilogram spacecraft straight up from the Earth's surface to an altitude of 2 times. So let me draw that just a little bigger. So again, this is the radius of the Earth. We're going to go up twice as high, so we want to go up to this point, and we want to just lift something straight off. So we're going to take this thing, imagine it's like a box, it's got a mass, we're going to lift it up. We don't want to just say, oh, MGH, it's going to go up to this point. But the idea that we had to do some work to do that, we're going to have a change in potential energy. So I would say that the is going to be U final minus U initial. U final is going to be a minus big G, the mass of the Earth, mass of this satellite that's going up, all over the radius of the Earth. But we're going up to twice that, so we're going up to 2R. That's the final. We started from the surface of the Earth, so that's going to be minus big G M all over the radius of the Earth itself. And so we can get a change in potential energy, and this is going to become plus, and we're going to have a +1 and a -1/2. I think you're going to see it's a big G M all over 2R when you do the math. Just convince yourself that this will be true. You can stick in the numbers. I've done that. You've got it on the sheet here as far as sticking in the numbers. You can check on that for yourself. It's like 6.26 times 10 to the 10th joules of energy. And this just lifts it up there. Okay, and then in part B, how much additional energy must be given to the spacecraft in part A to put it in a circular orbit at an altitude of 2 times the Earth's radius? Ooh, wait a second, I messed up. And it's probably a good thing. The idea of this I didn't read clearly enough. He says we want to go from the Earth's surface up to an altitude of 2 times the Earth radius. Now when he says altitude, this is the distance above the surface. So I messed up. So I want to go up, the altitude is going to be 1, 2. So this is 2 times R up above the surface. Now, how far is it from the center, though? It's going to be 3R. Okay, so the change in the potential energy is going to be final minus big G M all over 1, and 2 is 3 times the radius of the Earth, and then minus the initial, which is a minus big G M. That started at the surface of the Earth itself. And again, you can stick in the numbers and do that, and you'll get the answer. I'll just leave it as a question mark. Okay? Yeah, this issue, watch for this language. Usually when we do gravitation, we want to do it from the center. If he uses the word altitude, that implies that it's being measured from the surface up. Okay? Part B, how much additional energy must be given to the spacecraft to part A to put it into a circular orbit at an altitude of 2 times? So it's up here also. We want to put it into orbit, so I need to give it some energy for that. Now, the different ways we could do this, I would say that the energy for a circular orbit, that is the total energy as I derived and I have now erased, was minus big G M all over 2R. That would be the equation for total energy. Excuse me, this R is, this would be the total energy at the surface of the Earth. we want to put it in for the fact that I'm not r away, I'm 3r away. Let me write this, and I'm realizing this is kind of a mess. I've got the 1/2 here, so again, this is the circular orbit. Then I want the radius of the orbit, which is not r, but 3r. And that would be the total energy out at the farthest point. Maybe I'll call that E final. Then comparing it to E initial, well, I'm not going in orbit there. This is strictly the total energy for a circular orbit. Maybe total energy has to be this. So the idea that we're going to change energy, the original energy here is going to be, well, let me write it out. E final has got to be big G m all over 6r. Okay. And this one, let me, I'm not going to stick in the numbers, but let's just look at this. This minus and minus makes that a plus. I can make this 3r by multiplying that by 3. And so I'm going to have 3r, and I'm going to have a 3g minus 1 will be a 2gmm. And that's the change in the potential energy to get it up here. Then I need some additional kinetic energy to get it in orbit. So the idea that this is the total energy when I get it in orbit, that should be equal to the change in the kinetic energy, okay, that's the amount to get it moving, plus the initial energy that it took to get it up here. That's the potential energy. So kinetic plus potential, and that potential would be the 2 big G m all over 3r. So that is that term. Okay, so he's got some trickiness in here. Again, first, he did, if this is the total energy to put it into orbit, this puts it in orbit with both the change in the kinetic potential energy as well as the increase in the kinetic energy. Okay, so that total energy should be equal to kinetic plus potential. So we've kind of done it in 2 steps. So we've done this much first, then we're going to add some kinetic energy, and then that should give us a total energy for a nice circular orbit, which is required here. And then we can go ahead and solve for that kinetic energy. Okay. Didn't look carefully enough. This is a little twists on the way he states this stuff. He can get tricky. Okay, then there's a part C. Yeah.
In your notes or your solutions for it, you have K minus G and would that be the same as plus 2 GM?
I'm sorry, I'm not following what.
For that B on your
here?
Energy total equation, setting it equal to the change in our kinetic energy.
Oh, yeah.
You have then minus GM m over 3r instead of 2GM.
Oh, excuse me, I messed up here. This is, yeah, 3, yeah, this. Yeah, potential should have increased out here. So you see, I think this should be, well, this is going to be positive. It's got to be negative, so I've messed up. This is going to be final minus initial. Oh, it was just R, but then to get a common denominator, I put a 3 here and a 3 here. And so that leaves me with a 2 over 3. the change in potential energy needed to go up. The total energy needs to okay, this has to be the total energy. That's good. And it should be a mix of kinetic. Potential should be negative. I'm not sure where I'm... Yeah, the change in... Oh, yeah, thank you. Yes. Yeah, that was the change. Very good. Okay, this was the change in potential. It went from here up to here. That is a rise. That is plus. That's good. But I don't want the change in potential here. I want to get the potential right there. So the kinetic, let me say that this is the kinetic energy up here plus the potential energy. The potential energy up there would be this term, a minus M all over 3R, okay? Yeah, it should be negative. Yeah, this should be negative, okay? And that's the total energy. That should be equal to whatever kinetic energy I need. So he's having us figure this out separately. And then the potential energy, not the change in here. Consider we're already up here. So that is the potential energy where we're at. Yeah, so again, 2 steps. First was a change in potential energy up to there, and now we want to add some kinetic energy, and the potential energy is already that. So then we can solve for the kinetic energy. Wow. Okay, I should have...
We're not looking for a change in kinetic energy?
Well, we're assuming that they lifted it straight up here, so the thing isn't moving yet. And so the idea that we're going to get it set into motion, then we're going to give it to some kinetic. So this kinetic energy will be equal to the change in kinetic energy, since I'm starting from rest. Okay. Okay, actually, sometimes when I blow things and you catch it, that leads to some good things, because these are obviously things that I can make a mistake and do, and then certainly students can make a mistake and do. Once you have your kinetic energy, you can get the speed. In fact, once we have kinetic energy, what was the kinetic energy? Let's just put it down here. 8.91 times 10 to the 11th joules. We can then lead to the velocity. This is the velocity that it's orbiting. And we're going to use that in the next part, which is why I want to write that down. Orbital speed of the Earth is orbital speed of the craft is going to be 4.57 times 10 to the 3rd meters per second. And that should be the orbital speed that this thing has to go to be in a circular orbit. Oh, okay. Now one more twist. Okay, how much minimum additional energy would be needed to blast off from this orbit and escape the solar system? So the idea is we've got this amount of energy, and we want to escape. Actually, we can kind of focus right in here. Now, he's got a kind of a twist in there in that he wants to, how much additional energy would be needed to blast off from this orbit and escape the solar system. So right now he's in orbit around the Earth. So let's take a look at this. We've got the sun. We've got this thing orbiting the Earth. And this is the Earth, and this thing is going around the Earth. It's got some velocity to it, and that's what I'm thinking is his orbital velocity, 4.57, and that's times 10 to the 3rd meters per second. That's the speed of this thing. Now the thing is that the Earth is also going in the same direction. The velocity of the Earth And we would need to find that. The idea that we need to get the velocity of the Earth. He gives you the Earth, the radius, Earth to the Sun distance, and we can play with this distance is equal to velocity times time. And I know the distance here, let's call this the radius sub O, or the Earth's radius. That's going to be, the distance around is going to be a distance of 2 pi times that Earth's radius is going to be equal to the velocity that the Earth is traveling around here. So we've got both of these things in motion. And that's, I want to solve for that. The time going around, we know that it goes around the sun every 365 days. And of course I need to turn that into minutes and seconds to get the velocity of the Earth. And I think you can all crunch the numbers. I get a velocity of the Earth of, okay, this is 2.99 times 10 to the 4th meters per second. So that's how fast that's traveling. So the idea that the actual speed of the spacecraft is not just the orbital speed going around this way, but also the effect that the Earth is, it's going along with the Earth. And so the total velocity is going to be the sum of the two, the velocity of the spacecraft around the Earth plus the velocity of the Earth, and that would be the total velocity. And of course we can add these two together. I'll just put a question mark what that is. Okay, once we have that, then we can start to look at, well, what is the total energy? Total energy is going to be the kinetic energy of this thing, which is going to be a 1/2 m. And in this case, it's going to be the sum of these two velocities, velocity of the spacecraft around the Earth plus the velocity of the Earth itself. We've got to square that. We've got a potential energy term between the spacecraft and the Earth. That's going to be a minus big G, the mass of the Earth times the mass of the satellite, all over, this is at this distance of 3r, so that's going to be 3r away. Then we also have this thing is some distance from the sun. The sun has got a powerful mass, a force of attraction through its mass. That's going to be minus big G, the mass of the sun times m, all over, not 3r, but the radius here. That would be the radius of the Earth's orbit. You could say, well, it's the radius of the Earth's orbit plus this other little bit. I think if you actually crunch the numbers, you could throw it in there. It's going to be so small, it's going to be like your 8th or 9th decimal place. So you don't really need that. But the big thing is, it's got this amount of kinetic energy already. It hasn't escaped. It's got this potential energy. It's kind of sitting in the hole with both of these. So it needs to lift itself out. And we will need some additional energy. So I'm going to say plus delta E, because right now it's just orbiting the Earth and going around the sun. It hasn't escaped from anything. But this total energy of this thing needs to, when we add in that additional energy, what does it all need to add up to? 0. So then it's a matter of sticking in the numbers and solving for that delta E. Yeah?
Can you explain what VT is?
Oh, V, oh, I meant this to be V total.
Oh,
total.
So like, it's just like just the velocity of the spacecraft flying around and moving?
Right, right. They're both, the Earth is moving this way, and around the Earth, this spacecraft is going. Now, it could be more complicated than this because it's changing direction. The thing is, we'd want to blast off when the two are working together so that the two components add directly, giving us the largest possible V total, and that will give us the largest possible kinetic energy. So this is kind of helping us on the way in that this is positive, and these two are sitting us in the hole, so we have to dump in some more energy to lift it up to 0 energy. And so that's what I need to do to escape not only the sun, but the Earth, and get this orbiting craft out of here. So, okay, I think this, going to bumble through there, but I think the mistakes are ones that could easily be made by anyone, as I just did. So you can see that it's kind of tricky the way this is. Okay, let's see, we've got a couple of other things. As far as we've got chapter 14 to deal with, I think we've covered a few examples of 13 and 14, and you'll definitely want to do some of the homework related to that and see how well that works for you. Let's jump into this fluid stuff. And this stuff is a little easier. It comes, yeah.
Sorry, do you know if our file is the same weighting as our other exams?
It's not, it's like 25.
It's double, right?
No, our usual one's like 16.7.
Okay.
Right, and if he's going to do 2 problems, what did he say, 5 or 7? Sometimes they're easier problems than the midterms. That's why study. What's that?
The 2 problems would be 40%. So.
Oh, 40. Okay, so you can work that out. Okay. 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 Let's see. As far as fluids. Okay, and I've got, don't forget anything. Okay, let's just start off with the idea of pressure. This is something new. This is kind of fun. This thing is about 8 inches by 8 inches, and the air pressure in this room is like 15 pounds per square inch. Whoop, shouldn't let go. Wasn't going to let go. Do this right. If we try to figure out what force it would take to pull this thing off of here, that is, as long as the seal holds. I've got some things underneath. As soon as you let air in there, then it lets go easily. But we have each square inch, if you imagine breaking this thing down, 8 inches by 8 inches is going to break you up into 64 square inches. And you've got 15 pounds on each square inch. So do the math, but it's over 900 pounds of force would be holding this thing in place. Other than, I'm losing my seal here. Yeah, once the seal is set, it's strong. But I did this as kind of a graphical example of this idea of pressure. Pressure is so many, in this case it was pounds per square inch. Usually what we'll write it in terms of Pascal, and that pressure is going to be, let's say usually we'll do it in SI units. So 1 PA, this is a Pascal. And that's going to be equal to, we want to get pressure is going to be equal to a force over an area. And so that's going to be a force of 1 joule, 1 Newton, excuse me. My mind's starting to eclipse here. 1 joule. All over the area will be a square meter. And so that's going to be the unit of pressure. These units can kind of help you get set with what you need, like when you're setting up problems. Very often we'll express force is going to be pressure. Pressure times the area will be the force. Very often we use it in this form. So anyway, let's use it for some problems here.
Joules per square meter or newtons?
Newtons, okay. I put down joules, and then I caught myself. I said it, and then put back joules up there. The problem is in my mouth and my head. I'm trying to do this, and they don't agree. So thanks for checking that. 1 Newton of force per square meter. Okay. You ever have a day like this? I have them all the time lately, so that's why I got to retire. Okay. The problem is I'm trying to do this and talk and think at the same time, and it just doesn't work. Okay, let's do a fluids example, since this chapter is based primarily on fluids. This idea of pressure, though, will get used a lot later, so you definitely want to get comfortable with that. The idea that, let's say we've got water here and go down some depth, and let's see, I got some kind of depth here. Hopefully this looks sort of okay 3D. There's going to be, let's say, some area to this thing. I'll just call it area A. And it's got some height to it. And the idea that the pressure down here is wanting to, in a sense, hold this stuff up. That pressure down here times that area will be equal to a force. And that force would be the weight of this water wanting to push down. So the idea that weight is the density of water times the volume of all this water that's piled up. That's going to be H times A. And so that's volume times this is the mass of the water. Density times the volume times G will be the force of the weight of this on this. And this is being held up by the pressure of the water. And so notice this area cancels. So we can express the pressure is going to be the density times H times G. Or a lot of times, I don't know, a lot of times we say it, rho GH is going to be the pressure. The density we dealt with earlier, like chapter 1 is when we were first exposed to that. The idea that the density of the material is the mass over the volume. And the original definition of kilogram was based on a liter. A liter is centimeters, 10 centimeters by 10 centimeters by 10 centimeters. If you think about a cubic meter, one of these things is defined as a liter. And the idea that the original definition of a kilogram was a liter of water is 1 kilogram. So you pick up a liter bottle, that's a kilogram. You can feel it, like 2.2 pounds. Very often we want to do things not in terms of liters, although problems a lot of times get stated this way. We want to do it in terms of cubic meters. So a cubic meter would be a meter, a cube with a meter on the side. And for these things I could take, I could stack 10 of these this way, 10 of them that way, that's 100, and I could stack them 10 high. So there'd be 1,000 liters in a cubic meter. And so what's the density of water in terms of cubic meters? It's 1,000 kilograms per cubic meter. So yeah, so density of H2O is going to be 1,000 kilograms per cubic meter.
Is that something we should memorize?
Yeah, that would be something. Yeah, I think might expect that you just know that. You maybe know from, if you've taken like chemistry, that if you go all the way back here, if this is a kilogram, a little cubic centimeter is actually a gram. So, yes, a gram, and there's 1,000 grams here, or a kilogram. So sometimes densities get stated that way in terms of how many grams per centimeter, cubic centimeter. Okay, now for this, okay, so that's it. Okay, now the idea that you're likely to get in a problem is going to be typically a buoyancy type problem. It's either with something that's, let's say, going to just totally float on its own. Okay, you saw him do this, right? Okay, when he took the rock, I dumped this rock in the water, it sinks, right? If I tie this string on and hold this thing, it still gets lighter, right? There's a buoyant force. And you guys did the lab, so I trust that at least have an idea of what that is. Now let's look at the idea, though, behind this idea. Suppose we have, let's say this is, well, let me go back here. We just have some water at some depth here. And I've got this rock in here. And it turns out this rock could have any kind of shape. We're going to support it with some forces. Let's say I had that scale working properly. I'm going to have some kind of tension here, and this is what the scale is going to read. Gravity, of course, pulls down on this thing. This is going to be mg. But then when it's in the water, we're going to have some pressures that are helping to hold this thing up. The pressures are going to be more underneath because they're deeper, larger forces, and we're going to have all kinds of forces even pushing down on this thing from above, but these are going to tend to be weaker. And the overall sum of these forces should be what we call the buoyant force. Now, the buoyant force are these things. Now, if trying to get a sense of what they are, if I imagine taking the rock away and having water fill that back in, and I look at the water with that same volume or shape, it's being supported by the same pressures that are applied to the rock. Now, this water is in equilibrium. The water itself, let me just kind of draw that on the side, has got to have its own weight. This is going to be the mass of the H2O that's there times g, that weight. And then this other force that's acting on that, holding that in position, is going to add up to be the buoyant force. So that buoyant force, since it's being just holding this water here, that buoyant force is equal to the weight of that water, the mass of the H2O times g. That's going to be the buoyant force holding this thing up. If I take the water out of there and stick the stone back in, I've got the same buoyant force. And so Archimedes' principle is that the buoyant force is equal to the weight of the displaced water. Let's just launch into a quick problem here. I think there's several here. 4 is here, but I think 5 is one that would be probably the best to look at. Got water. I'm going to take a block of wood, which we don't know the density of right offhand. We're going to take this block of wood, we're going to put it into the water, and he says that this cube, I guess it's a cube, 15 centimeters on the side, and it's going to float with 45% of the wood block above the water line, and that would imply, if this is 45%, that this is 55% below the water line. And the idea that there's going to be forces on this, we're going to, one, displace this amount of water, and the forces that are going to be acting are going to be the buoyant force, and then the weight of this thing, that'll be mg for the block, and it's just floating there. So now he's going to ask, but let's first deal with this. I want to get the density of the wood block. Clearly it's floating in the water, so some of it's sticking up. And so in this case, I'm going to say that the buoyant force minus mg has to be 0. Some of the forces have to be 0. The buoyant force is equal to mg. The buoyant force is equal to the weight of the displaced water. Okay? Let me... Okay. Okay, the buoyant force, the weight of the displaced water is going to be the density of water, which we know. That's the 1,000 kilograms per cubic meter, times the volume of this thing. Let's just call it, well, okay, it's going to be 0.15, 15 centimeters cubed will be the volume of that. But there's, it's only 55% of it is below water, so it's going to actually be 0.55. We're going to multiply that. That's the volume that is below the water times that density times G. That should be equal to the mass of this block, which would be, let me do it this way, as the density of the wood times the volume of the wood, which is going to be the whole cube, 15 centimeters cubed, times G. And from this, I can get the volumes cancel. I can get that the density of the wood is equal to the density of water, which is 1,000 kilograms per cubic meter, times 0.55. So the density of the wood would be 550 kilograms per cubic meter, density of the wood. Okay. Once I have that, then now what he's asking now, he says he wants to stick some lead up on top and sink this thing down. He still wants it to float. So the block itself is going to come down. We've got the water level. And the block, now the way he stated this, here's what he means. When I first did it, I just brought the block down to this level. He means the block should be totally submerged. And then on top of that, he's got the lead sitting, a certain volume of lead. And he wants this whole system just to hold. What volume of lead can be added to the top of the wooden block without sinking the wood-lead system? So this is just barely floating here. This is going to be the volume of the lead that we need to get. He does give us the density of lead. We have the density of wood. And so then we've got the idea that this thing is floating. So we're going to have the weight of both the wood block as well as the lead, and then we're going to have a buoyant force, and that buoyant force is we're displacing the block itself plus the volume of lead. So let me write this out and see if you're okay with it. I'd say the basically the buoyant force is equal to the weight of the wood plus the lead. And that buoyant force is equal to the weight of the displaced water. So that would be 1,000 kilograms per cubic meter. That density times the volume of lead, or let me put this as 0.15, 15 centimeters cubed, all of the wood block, plus the volume of the lead, and times G. So that's the density times the volume, that's the mass, times G is the weight of the displaced water, is equal to the weight of the wood plus the lead. The density of the wood is going to be this 550 kilograms per cubic meter times the volume of the wood, which is 0.15 times, and that's cubed, that's meters, and plus the weight of the lead, that's going to be the volume of the lead times the density of the lead. He gives that as 11,300 kilograms per cubic meter. That's the density times the volume of the lead, and of course that's the question, what do I have? All of that, well, these two things should be equal. you need to solve for the volume of the lead. Now notice I've got it on both sides of this equation. Still not bad. It's linear. You can do the math, but basically we want to solve for the volume of the lead. And that would be the basic setup for that. Okay, so that's...
Does that not have gravity on it too?
Oh, yeah, that should. Yeah, it's the weight. Thank you. G, G. And the G's very often cancel. That's why I sometimes forget to write them down. Okay, but thank you for catching that. Okay, wow. A lot of stuff here. Now, there's one other possible issue that he could hit. Typically, you'll get a kind of a buoyancy density kind of problem is typical of what he might do. Also in this chapter is going to be fluid dynamics. Once you get fluid to move, and he developed, I think, was Bernoulli's equation for that. That has to do with flows. That is, fluids that are in motion. All of this is what we call fluid statics. Nothing's really moving. Everything's at rest. Everything's balanced. So this next one is typically they represent this thing graphically this way. Bernoulli's equation is very specialized. It's not very applicable to most real-world situations, but the idea is that if you have, let's say, a pipe and you've got different cross sections, let's call this A1, this one call this A2, and we're going to get water to flow through this thing. This needs to be it's totally frictionless. There is no heat generated. It's what we call perfect laminar flow, that the flow has no chaotic motion to it. It's very smooth. That's why we need to have this transition very smooth. There's going to be maybe a pressure at this side. We'll call that P1. There'll be another back pressure at this side. We'll call that P2. There'll be a particular rate this can flow. The idea that if this comes in here, it can undergo, let's say, this little bit of water here, water or some kind of fluid, is going to be, let's say, delta x1. That is going to, if that pressure moves that water here, it's going to then move the same volume of water out. And this would be a little delta x2. I expect these two volumes to stay the same. So this volume will be this, would be the volume of this. This is going to be A1 times x1. And then there'll be another volume over here. That's going to be equal to this same volume. That's going to be A2 times x2. And one thing that we can do is the flow rate is equal to volume that moves in some time delta t. Volume, if you think if the practical example would be how many gallons per minute, it would be the volume in the time. And that's something called the flow rate. Or how many liters per minute or second. I can take this and divide by delta t, so that's A1, x1 over, and I'll put the delta t with that, is equal to A2 times x2 all over delta t. This should be the velocity of down here at this point, where this is going to be moving with some v1. And so this is going to be A1 times v1 will be equal to A2, and x2 times delta t would be the rate that the water is moving here. That's going to be times v2. So this is what we can call this the flow rate. And this is a handy thing to use. Now, we often use this in conjunction with Bernoulli's equation, which Doctor, I'm not going to take the time to derive it now. We're kind of running low on time. Bernoulli's equation is this. The pressure times this area is really a force. So pressure 1 is acting like a force, is going to take this water, it's going to move it up so it can lift its potential energy. So it's going to be mgh, but we'll put this in terms of the density of the fluid, or in this case H2O, the density times times G and times H1. And then plus the kinetic energy is going to be a 1/2. Normally we'd say mv squared, but instead of mass, we're going to have the density of the fluid times v1 squared. And then that's going to be equal to, I'm running out of room here, is going to be this, which is going to be P2 plus the density of the fluid times G times H2 plus 1/2 rho times V2 squared. And so these two things are equal. Kind of initial and final. So what is the pressure here? What is the speed that it's moving? It's got some kinetic energy. It has maybe some potential energy above some point. Up here we got the same thing. We've got a pressure, we've got a velocity, we've got and a potential energy. It's lifted up some distance h. And so those are our possibilities. Okay, so we can make use of these dynamic equations in doing problems. And the one I've got here is this number 6. It's a water main pipe coming into the first floor of the PS building. Is 2 inches or 5.08 centimeters in diameter. The water line carries the water up to the second floor 4 meters above. So this is going to go up 4 meters. And okay, assuming the water line's diameter remains constant, what is the drop in pressure between the first and second floor? Let me kind of summarize that on over here so that we don't get things mixed up. Okay, so again, let me write this. P1 plus rho g h1 plus 1/2 rho v1 squared is equal to P2 plus rho g h2 plus 1/2 rho v2 squared. Now, first off, if the diameter doesn't change, first of all, we got two problems. The water line, assuming the water line's diameter remains constant, what is the drop in pressure between the first and second floor? That is saying, if the diameter is the same, that's saying that A1 is equal to A2. And so and I know that A1 V1 is equal to A2 V2. So if these two things are equal, V1 should be equal to V2. So that's the first thing I would conclude. If those two are equal, then I could go ahead and get rid of that term. Okay? And then it's a matter of what is the drop in pressure. Okay, so the drop in pressure would be the pressure difference between this. So this is delta P. This is actually what he's asking for. What is the drop in pressure? That would be P1 minus P2. And so I'm taking this back over to here, P1 minus P2. I'll take this over to the other side. That's going to be rho G, and I'm going to have an H2 minus a rho G H1, or better yet, just say rho G H2 minus H1. And we can get that difference in pressure. He tells us the height of the going up 4 meters. We have the density of water. We've got that. We can get what delta P is, and that would be that drop in pressure. You will see there's cheaper ways, easier ways to get it. We could just say it's rho GH, basically, is the difference in pressure. So you could maybe just get that without employing Bernoulli's equation. Now the next part, though, he changes things. He says, if in addition to being 4 meters above the first floor, the pipe on the second floor is corroded so the diameter is reduced by 30%. Okay, so this is not so simple. He'd say, okay, you've got the area 1. He gave us the diameter. We better keep track of this. On the first floor, that's A1. A1 is equal to, not equal to A2. A1 is equal to pi r squared. R should be this 0.0508 centimeters, that's meters, divided by 2, because that was the diameter, and I need to square that. Okay, so that would be the area of the first pipe. And then the area of the second one is going to be, what, reduced by 30%. So that's going to be, if it's reduced by 30%, does that mean, is this okay with you? 0.70 or 70% of A1 should be equal to A2. Okay.
Because it's the diameter, not the area.
Oh, whoa, wait a minute. Yeah, thank you. Yeah, I'm getting sloppy here. You bet. Yeah, it was not you said 30%. The diameter is reduced by 30%. Very good. That's going to be pi. And so when we put that in here, this is going to be 0.70, 70% of 0.0508 over 2 squared. Okay, and it's better that you do the math here. I think I've got it right on the other side, so you can check that out. But then once I have this, then I can make an argument for V1 and V2. I can say A1 times V1 is equal to A2 times V2. And he does tell us that the water is flowing at a rate of 11 meters per second on the second floor. So this would be V2, 11 meters per second on the second floor. From that and these relationships, let me just put V1. I want to be able to get that velocity on the first floor. Okay. Then I can go ahead and let me go ahead and put this up again. P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. And he wants to get the pressure difference again, so he's going to want to go P1 minus P2. We could make our potential energy, let's just make the ground floor, let's just make that 0. Then this H would then be 4 meters, since it's up 4 meters. And so I'm going to have 1/2 rho, I'm going to have a V1 squared plus rho G times 4 meters plus a 1/2 rho V2 squared. And of course I need these figures from here, so I've got V2, that's 11 meters per second. V1 I'm going to need to take all the way back here. And then I have the rest of this laid out. I should be able to get what that drop in pressure is. So, tricky problem how he's putting that together.
Negative in there?
Yeah, it should be.
Could you move one thing over and make it negative?
P1 should be a higher pressure than P2.
Yeah, but what about moving the 1/2 rho V1 squared?
Oh, where am I? Where's
There,
up here?
to the right side. You subtracted P2 over to the left side and you moved.
Oh, I brought. Oh, you're right. Well, okay. Oh, yeah, this should be coming over here. This should be negative. Yes. Yeah, thanks for catching that. Okay, and then we get our drop in pressure between those two. Okay, whew, okay, boy, he's going strong to the end. Hopefully you do too. I know I am not. Okay, for the rest of the afternoon, anybody that hasn't been with the Friday sessions, you're welcome to come on over PS 116. We're going to be working, getting ready for the final. Again, I don't do a comprehensive review. I do have the previous reviews online, but I think probably at your best bet is to dig in to these problems and work them. All your past exam questions, also these ones we've passed out. Try to study from those. I think those are going to be your best preparation. And good luck. Monday morning it comes bright and early. So, okay. All right. Thanks and good luck. So.
Don, can you give you chapter 13 homework?